So it appears that nobody likes question number 6. Well, I guess we can go through it. Let's give it a try. First of all, this is a strange question because it gives us all the answers to start with. Normally in one of these Hardy-Weinberg problems, the question asks you to calculate the heterozygous and the question asks you to calculate the homozygous dominant. Well, all of that information is already given to us here, which is a little bit odd. The other thing to look out for here is that this is a incomplete dominant situation. So we don't really have a dominant, we don't have a recessive. So what we can do is just sort of arbitrarily assign one of the homozygous genotypes P and the other one Q. Which one we choose doesn't really matter at all. So I'm just going to say, in this case, I'm just going to say black is Q. So I'm going to say that Q squared is going to be 980, which is the number of black gerbils divided by the total. So the total is 2000. That's just adding them all together. Okay, and that's going to give me 0.49. I can then figure out Q is equal to 0.7. P then would be 0.3. So now what do I do? Well, what I'm going to do is I'm going to pretend to do a normal Hardy-Weinberg problem. So what I'm going to do is try to figure out, how many heterozygous should we have if Q is 0.7 and P is 0.3, and how many homozygous of the other type. Normally we'd call it homozygous dominant, but in this case it'd be homozygous white. Should we have, which is going to be P squared times the total. So why don't we do that first? Let's see if 180 actually is the correct number for the white. Let's see if P squared times the total actually is 180. So I'm going to say the number of white ones, or I don't know what you'd want to call them, WW, is going to be P squared times the total. So that's 0.3 squared times 2000. Well, 0.3 squared times 2000 is indeed 180. So since this 180 and this 180 they're the same, that sure looks like this is a Hardy-Weinberg equilibrium, because they need to be the same if that's the case. Let's just double check the heterozygous too. It's going to be 2PQ times the total. So it's 2 times 0.3 times Q, which is 0.7, times 2000. And if we're doing this correctly, this should be 840. So 2 times 0.3 times 0.7 times 2000 actually turns out to be 840. And since this 840 matches up with this 840, we can then say, yes, we have a Hardy-Weinberg equilibrium. Now most of the time, so clearly I set this up so it would work out. I purposely set it up that way. But most of the time when you're looking at a random sort of a population that you run across and you look at the numbers, odds are they're not in a Hardy-Weinberg equilibrium because of all those 5 conditions that could be violated. So let's say instead of 180 here, I got 250 of these guys here, 250 white individuals. But it's supposed to be 180, we would then say, well, 250 is not 180, therefore no. Or let's say if this is 840, and instead we got, I don't know, 1100 or something like that, we would say, nope, they don't match up, they're not the same, therefore no Hardy-Weinberg equilibrium. All right, hopefully that clears things up, and hopefully that number 6 isn't as difficult now.